In this hour, we will talk about detectability, which in a sense is a generalized version of, or a less restrictive version of observability. Okay, so we will try to motivate this notion, this property of a system through the observable decomposition. Okay, so suppose we have an unobservable system. Okay, which we represent in observable decomposition. In observable decomposition form. So we have x dot equals the A matrix times x plus BU, and y equals the C matrix times x plus DU. Okay, now let's consider the vector, the state x, as composed of two pieces, two subvectors, namely the observable part and the unobservable part, or the state corresponding to observable dynamics and the state or the substate corresponding to unobservable dynamics. For observable dynamics, we have the notation XO, and for the unobservable dynamics, we have the notation XU. Okay. So x dot equals, this is the A matrix of the observable decomposition, A21 AU. It's lower block triangular. It's in lower block triangular form. XO, XU, XO, XU. The observable decomposition makes no claims on the controllable properties, so therefore we have a general or a B matrix without any particular structure. And as for the C matrix, we have CO here and 0 corresponding to the unobservable dynamics. Okay. Now, we know that by definition of observability, if we know the output and the input, we can determine the evolution of the observable part of the state, namely XO of t. Okay, so let's put that down. We can determine based on our knowledge on y of t and u of t. So why is it reasonable that we assume we know y of t and u of t? Well, y of t corresponds to, in general, the measurements. Therefore, those data we collect from our sensors, and u of t, that represents the control input that we apply to our system. Since it's us who is applying that signal to the system, it's obvious that we know what it is. Okay, so we know y and u, and system, the observable part by definition of observability, can be determined, okay, using those signals. Okay, the observable part of the state, which we denote by XO of t. Okay. Now, how about the part of the state corresponding to the unobservable dynamics? Okay. So again, from the very definition of observability, by observing input and output throughout some interval of time, we cannot exactly determine what XU of t is, okay, could be or should be. But still, let's try to let's try to make some conclusions regarding the behavior of xu of t, or our knowledge on xu of t based on the system parameters. Okay, so how about xu of t? So let's write the xu dynamics or xu subdynamics. Xu of dot equals au xu plus the term that represents the effect of the observable part on the unobservable part, a21 xo, and we have plus bu u. Okay. Therefore, we can consider, well, this is a linear system where these are the self-dynamics, and these two pieces can be considered as the external input to this subdynamics. Therefore, we can write the solution, the expression for the solution of xu of t. Xu of t equals the state transition matrix corresponding to this A matrix. This is unobservable, AU, okay, times the initial condition for xu plus the integral that represents the external effects on the dynamics. Namely, we have e to the AU of t times the initial condition, okay, plus the external input effect from 0 to t, e to the AU t minus tau a21 xo tau plus bu u tau d tau. Okay, now this piece here is known. Why? Here we have the input signal, okay, because it's the control input, we know what it is. Here we have the substate corresponding to the observable part. Since it's observable, we can compute what this is based on our knowledge on y of t and u of t. Therefore, all the signals here are known. As a result, this integral can be computed. That means this piece we can compute, okay? So that's known. However, this part is unknown because there's no way that we can determine exactly what the initial condition for the unobservable part of our system is. Okay, now, so that means that we will never be able to figure out xu of t exactly, okay? But perhaps we don't need to determine what xu of t exactly. An approximate knowledge would be enough. And that approximate knowledge can be obtained provided that the matrix representing the unobservable dynamics is exponentially stable, okay? By which I mean that all the eigenvalues are with strictly negative real parts. Okay? Because if that is the case, if AU is a stability matrix, then e to the AUT is converging to 0 exponentially fast. Therefore, even this term is unknown due to the initial condition. And even though initial condition could be arbitrarily large, as time goes on, this exponential decay will make it more and more insignificant. Okay? So after some time, xu of t will be very close to this term, which we can compute. Okay? So even though xu of t we cannot figure out, okay, at the beginning of the time, but as time goes on, we will have a very good idea what it should be, okay? Because if, of course, this AU of t is with all negative real parted eigenvalues. And that will eventually motivate us to define a detectable system. Now, let me repeat what I just said. Suppose now that the matrix AU is with eigenvalues that are all with negative real parts. Okay, informally, I'm going to call that A exponentially stable. Okay, then e to the au of t x u 0 converges to 0 exponentially fast. Okay, that means we don't have to wait too long to assume that this is now negligible, that term, and that allows us to claim that after some time xu of t approximately equals, and as time goes on the approximation becomes better and better, okay, equals the term that we can compute, the known term. From 0 to t e to the a u t minus tau a 21 xo tau. Okay, the integral for t large enough. Okay, so in other words, xu of t becomes eventually known. Okay, so if xu of t becomes eventually known and xo of t was known from the very beginning, because that corresponds to the state of the observable part, so that means the entire state xo and xu stacked together, considered as a single vector, becomes eventually known. Okay, so therefore, if au is exponentially stable, this system, even though it's unobservable, is in a sense eventually observable. Okay, so it becomes in a sense observable if you wait long enough. Hence, the whole state x of t x u of t becomes eventually known. Okay, if this is satisfied exponentially stable. Okay, and that motivates the definition of eventual observability, which we don't call eventual observability, but we call simply detectability of a system. And the definition, what the definition should be is now more or less clear. A system is said to be detectable if in its observable decomposition representation the AU matrix is exponentially stable. Okay. So for continuous time, that would mean all the eigenvalues of AU matrix is with negative real parts, and that definition has a very natural version for discrete time. In that case, we would require for detectability that all the eigenvalues of the AU matrix are strictly within the unit circle. Okay, now let's introduce our detectability definition, which is eventual observability, okay, or a more general version of observability. The pair CA is said to be detectable if either it's observable. In that case, the AU matrix would be non-existent. Okay, the system will directly be in observable decomposition. If either it is observable or its observable decomposition is such that the matrix appears, which represents the unobservable dynamics, is exponentially stable. Okay, here we're using the word exponentially stable in a general sense. For continuous time, it would mean all the real eigenvalues are with negative real parts, and for discrete time, all the eigenvalues are with strictly less than unity magnitudes. Okay, so this definition is applicable both to continuous time and discrete time, therefore. Okay. Now, it's not difficult to figure out that this detectability for LTI systems has a dual concept, okay, which we already studied, and it's stabilizability. Okay, in a sense, if you think about it, stabilizability was eventual controllability, and then therefore stabilizability and detectability, they are dual concepts of one another. Okay, so detectability and stabilizability are duals of each other. Okay, that's very nice from the analysis point of view, because, well, first of all, this means that if the pair CA is detectable, then and only then the pair A transpose comma C transpose is stabilizable. So because of that duality, we can obtain many very useful theorems for detectability by simply dualizing the corresponding results for stabilizability. And we're gonna quickly revisit or generate all the corresponding detectability results from our stabilizability tests that we studied earlier. Okay, that is the pair CA is detectable if and only if the pair A transpose C transpose is stabilizable. Okay. Now, let's, in the light of this duality, let's generate quickly detectability tests from their corresponding dual results in stabilizability. Let's begin with the eigenvector test. Okay, this is the eigenvector test for detectability. The pair CA is detectable okay, if and only if no eigenvector of A belongs to the null space of C, if that eigenvector has an eigenvalue that's with real part 0 or positive. So I'm talking about the continuous time case. So the pair CA is detectable if no eigenvector of A with eigenvalue real part greater than or equal to 0, and that can be translated to discrete time as the magnitude greater than or equal to 1 for discrete time systems belongs to null space of C. Note that if we forget about this eigenvalue constraint and say the pair, consider the condition that pair CA is such that no eigenvector of A belongs to null space of C. So that's our test for observability. Okay, now what we're doing is we're relaxing that test in the sense that It's okay for some of the eigenvectors to belong to null space of C as long as their eigenvalues are on the open left half plane. Okay. Otherwise, if the eigenvalues satisfy that condition, then they cannot be in the null space of C. Okay. In the null space of C, if we want our system to be detectable. Okay. Now here is another version of the eigenvector test, PBH test. Okay. The pair CA, where A is representing an nth order system, is detectable if and only if A minus A minus lambda I C equals n. Okay, so this matrix is full rank for all lambdas satisfying this condition. That's for continuous time, and this matrix has full rank for all lambdas satisfying this condition for the discrete time version. Okay, for all lambdas satisfying this. Okay, and for discrete time we have to check for the eigenvalues satisfying that property for discrete time. Okay, now let's also talk about the Lyapunov test. So this is the Lyapunov test for detectability. The pair CA is detectable if and only if we can find a symmetric positive definite matrix. Okay, such that the following matrix inequality holds: ATP plus PA minus C transpose C is a negative definite matrix. Okay, to say that we just put less than 0 sign. So this is for continuous time. For discrete time, this boils down to, not boils down to, but it becomes, or it should be constructed as follows: minus B minus C transpose C is a negative definite matrix. Okay, so this is for discrete time detectability. Okay, now to get an idea on why, for instance, the discrete time inequality is related to detectability, let's prove this one direction of this statement, okay, given in the Lyapunov test. So let's put it here. Okay. Example. Prove that if this condition holds for a discrete time system, then the system or the pair CA is detectable. So prove ATPA minus P minus C transpose C being a negative definite matrix implies that pair CA is detectable. Okay, now we're going to do this using the eigenvector test. For that, what we need is an eigenvector. Okay, so let AV equals lambda V. Okay, V an eigenvector. And since we're going to use eigenvector test, we don't apply that test to every eigenvector. Okay, we apply that test to eigenvectors for which the eigenvalue for discrete time is on the unit circle or outside the unit circle. Okay, so therefore the V that we're going to apply our test to must have a lambda such that lambda is, the magnitude of that lambda is greater than or equal to 1. Okay, so we're proving this result, and this is the discrete time Lyapunov inequality for detectability. Okay, so this implies that 0 V conjugate ATPA minus P minus C transpose C V. Okay, so what we did is, well, first of all, we reversed the inequality. We put the 0 here, and then we multiply both sides with V conjugate transpose from left and V from right. Okay, now here this was 0 matrix, now it becomes scalar 0, and this thing here must be negative, okay, because this holds true. Now let's play with the terms. This we can write as AV conjugate transpose. Since A is a real matrix, A transpose and A conjugate transpose, they are the same thing, and we can write V conjugate transpose times A transpose as AV conjugate transpose, and that's multiplying P. And then here we have an A, and that A is being multiplied by V coming from right, so we have here AV. And then we have this P, V conjugate transpose PV, and finally we have CV conjugate transpose times CV coming from this term. Okay, and this thing, and each of them is now a scalar. This three terms produces something that's strictly negative. Okay, now V is not an arbitrary vector, it's an eigenvector. Okay, therefore it equals lambda times V. So what happens here? Here we have lambda V, here we have lambda conjugate times V conjugate. Okay, so this lambda we can put it here. So, and what we have is lambda conjugate times lambda times V conjugate transpose PV. Now lambda conjugate times lambda itself produces the magnitude square of that complex number. Therefore this can be written as, okay, well, let me write it here, lambda conjugate transpose times lambda V PV minus V conjugate PV, and here we have CV conjugate transpose times CV. Okay, so this is lambda magnitude square. It's multiplying this, and here we have the same term here. So together these can be written as lambda magnitude square minus 1 multiplied by V conjugate transpose PV. Okay, and this can be written as minus norm square of CV. Okay. Okay, now what we know is that this is greater than or equal to 1, therefore this is greater than or equal to 0. This thing is positive because V is non-zero and P is a symmetric positive definite matrix. Okay, so this whole thing therefore is less than or equal to 0. Now take this guy to the other side, and what we have is norm square of CV is strictly greater than 0. And that means norm square must be strictly positive. That means norm should be strictly positive. And that means what's being normed must be different than 0. And that means, finally, that V does not belong to the null space of C. And then by eigenvector test, we conclude, therefore, that the pair is detectable. Okay, so this, let's squeeze it here, therefore that implies norm square of CV positive. That implies CV cannot be 0. That implies, and that reads V does not belong to the null space of C, and as a result we have detectability following from the eigenvector test. Okay, so that's, in the light of this demonstration, now it's a little bit clearer why this inequality is relevant to detectability. Now, if a pair CA is detectable, then we can make the matrix A minus LC by choosing a proper gain matrix L, a stability matrix. Okay, and that follows from the Lyapunov inequality. So let's put that observation down, which eventually will take us to the observer design. So let a pair CA be detectable. Then, by Lyapunov test, there exists a symmetric positive definite matrix such that, okay, you're talking about the continuous time case, suppose, such that ATP plus PA minus C transpose C is a negative definite matrix. Okay, now, using that P, we now introduce a matrix L as 1/2 P inverse C transpose. Okay, now, using this matrix, we will now show that the matrix A minus LC must have eigenvalues that are all with strictly negative real parts. So, starting from the Lyapunov inequality, ATP plus PA minus C transpose C. Okay, so that can be written as ATP plus PA. We write that C transpose C as 1/2 C transpose C plus another 1/2 C transpose C. Okay, one of the 1/2 C transpose C's we multiply from left by identity matrix, and we write the identity matrix in this funny form: P times P inverse. Okay, times C transpose C, and we have the other half, which we multiply by identity matrix from the right hand side, and we write identity matrix in this form: P inverse times P. Okay. Now, what's the use of making all those seemingly unnecessary steps? Here is the use, because if you write this sum of terms in this slightly more complicated form, you can reorganize the new terms in the following sense: A minus 1/2 P inverse C transpose C transpose times P plus P times this matrix, A minus 1/2 P inverse C transpose C. Okay, and then this matrix here, 1/2 P inverse C transpose, is what we're defining as L. Okay, so write it as L, and what we have is A minus LC transpose P plus P A minus LC is a negative definite matrix. And then by an earlier theorem, Lyapunov theorem, on exponential stability, we deduce, therefore, that this matrix A minus LC must have eigenvalues with all negative real parts. Okay, therefore, the system x that equals A minus LC times x is exponentially stable. Okay. Therefore, we can conclude the following. If your pair CA is detectable, then you can always find an L, a gain matrix, such that A minus LC produces an exponentially stable system. Okay, so let's put that observation down because it's important for the observer design. Okay, so this is our conclusion, which has quite important applications in practice. When the pair CA, okay, suppose that C is an n by n matrix and A is n by n. When this pair is detectable, then it is always possible to find a gain matrix L. Okay, that should be n by m. Okay, so C is n by n, L is n by m, so that their product LC is n by n, which it should be because we're subtracting that matrix from A. To find the gain L such that the matrix A minus LC is exponentially stable. Okay. Now that this is also true for the discrete time case. So that means if C and A is a detectable pair in the discrete time sense, then you can find an L such that all the eigenvalues of this matrix are strictly within the unit disk. Okay. Now the question is, what's the use of this theorem, at least from the practical point of view? And here is the answer. Okay. State estimation. Now, state estimation has to do with the following scenario. We have some system, x that equals ax plus bu, and from that system, we collect some measurements, okay, which we represent by or denote by y, cx plus du. Okay, measured or known are the signals y of t. Okay, the measurements coming from sensor, and we know u of t because that's our control input. So we know what we apply to the system. And suppose that the pair CA is detectable, so that we can find such an L, which makes A minus LC an exponential stable matrix. Okay. Now the question is, or the problem is, we want to figure out x of t, the actual solution of the state. We cannot directly look at it because it's not possible. Only we can look at, or we can measure certain things, a partial information regarding the state, and that partial information is represented by y of t. So therefore, in order to achieve our goal, we have to find some other way, some way of computation that produces x of t, or an estimate of x of t, an approximation of x of t from this piece of known signals, y of t and u of t. Okay, here is a nice solution. We start by choosing an L such that A minus LC is exponentially stable. And we can find such an L because the pair is detectable. Okay. Choose the gain, sometimes called observer gain, L, by M, such that A minus LC is with all strict negative real parted eigenvalues. Okay, informally we're going to call that matrix exponentially stable. Is exponentially stable. Okay, and such an L exists, it turns out, only when the pair CA is detectable. Okay, so therefore this statement is, the reverse of this statement is also true. There's an equivalence relation between the existence of L for this property and the detectability of the pair CA. Okay, and then once you have such an L, construct the following system. Okay, x hat dot equals ax hat plus bu. Okay, this is a new system, and this is an artificial system in the sense that it's running within our computer. So in order to run that in your computer, you choose an initial condition, okay, x hat, and then you solve the differential equation. Now there are two inputs to this system. One of them is bu term, which is the same input that's running, that's driving the actual system, the plant, okay, that's out there. And also you add to it a correction term, plus L times y minus y hat. Okay, now y is the measurement that you collect from the system, and y hat is what you compute using x hat information and the input information. Okay, where y hat simply denotes cx hat plus du. Okay, now this is called an observer. This is called an observer. Okay, once again, this is a system that's running numerically in a computer, within a software, or using a software, and it's such that it has the same system parameters A and B coming from the actual system. In addition, we have L times the difference between the actual measurement and would-be output, which we're calling y hat. Okay, and y hat is cx hat plus du. Now the nice thing about this system, because it's running within our computer, we know everything about it. Okay, in other words, we know exactly what x hat is. We don't have the observability or unobservability problem with this observer system. Okay, now it turns out that the observer system, output of which is x hat of t, is such that no matter how you start your observer from, okay, what initial condition you choose for x hat, and what initial condition the actual system has, x of 0, okay, for all those pairs of initial conditions, the estimate that's produced by the observer system, x hat of t, exponentially catches the actual state, x of t. Okay, so therefore, it's a very nice way of computing x of t. You're producing an estimate, and that estimate becomes better and better as time goes on. Thus, here is the claim: x hat of t, okay, which is produced within our computer, becomes closer to x of t exponentially fast. This simply means that take the difference, the error, that error is converging to 0 exponentially fast as time goes on. Okay, for all initial conditions x 0 and x hat 0. Okay, in other words, after a while, okay, you can, for all practical purposes, you can say, I know what x of t is, okay, and that knowledge will be produced by your computer. So x of t approximately equals x of t for large t. Okay, now let's prove this claim, where we have to use at some point the fact that A minus LC is exponentially stable. Okay, here goes very short and elegant demonstration. Define the error signal, that is, the signal that shows how good your approximation is at any given time. Okay, E is defined as x hat minus x. Okay. This is the estimate produced by your computer, and this is the actual state of the system, the plant, let's say. Let's try to figure out the evolution of E, and for that, a good way seems to be trying to figure out the derivative of E. Okay, so what's E dot? So by definition, E dot is x hat dot minus x dot. So that equals x hat dot minus x dot, and that equals what? Now x hat dot is here, and x dot is ax plus bu. So let's write that down: ax hat plus bu plus L times the correction term y minus y hat, and y was cx plus du, and y hat is here cx hat plus du minus cx hat minus du, and then we have minus x dot. X dot was ax plus bu, so we have minus ax minus bu. First of all, we have to note that these dynamics, the aerodynamics, depends only on the initial conditions and does not depend in any way on the input that you're using to drive the plant, because this bu is cancelled by this bu, and this du is cancelled by this du. Okay, and all that remains is the x hat and x terms. Now that can be collected in following form: a minus lc times x hat minus x. Okay, we have ax hat here minus ax hat here, we have lcx here minus lcx hat here, and all those can be collected in this simple expression. And once you do that, you see that since this was by definition the error, what you have is the aerodynamics, okay, depends only on the initial condition for the error, and initial condition for error is simply the difference between the initial conditions of the state, actual state, and the estimate. Okay. Therefore, we now see why the error should converge to 0 exponentially, because we obtain E that equals A minus LC times E. That implies, because this matrix is exponentially stable. Why? Because we chose L to guarantee that, and the reason that we were able to choose such an L was that the system or the pair CA was detectable. Okay, so this implies E of t converges to 0 exponentially fast. That implies the norm x hat of t minus x of t, because this is error, this norm converges to 0 exponentially fast, and as a result, after a while, and in fact after a short while, the estimate becomes a very accurate approximation of the actual state of the system x of t, for large t.